Hello, this is Group 3's final presentation. I'll briefly go through each of the major designs in our program. The first is mapping. The map was created using an SVG file with lines to represent the map boundaries. Map was divided into a grid using a four-way grid mesh where each node in the grid is 1 inches and connects to all adjacent nodes. So this will turn our grid into a 56 by 48 grid with the which corresponds to the lines that represent the map boundary defined in the SVG file. And the boundaries of the maps and the obstacle detection is done by removing nodes from the mesh where boundaries or obstacles exist. There's also a cushion to account for the size of the robot, for instance, so the map boundaries are 56 by 48, but because the robot is kind of large, 3 inches from every side of the map are removed to make sure that the robot doesn't run into any of the walls. The map X coordinate goes toward the other side of the board, and the Y coordinate goes across the width of the board. The movement. The odometry pose provider was the pose provider that we used. It was attached to a move controller and wrapped in a navigator. And this controls the robot's movement. So the pose provider is how the robot keeps track of where it is on the board. The move controller updates the pose provider, and the navigator wraps the move controller and allows to add waypoints, and specifically with our path planning is the navigator follows the path. The navigator by itself was not sufficient for accurately performing moves, so a function was created using the gyro sensor which assists the navigator with turns. Whenever a turn is made, the pose provider outputs a heading it thinks the robot is facing. This is compared to the gyro sensor, and if it doesn't match, the pose provider is updated with the actual heading and the turn is made again. So this way it's able to remove the errors by just kind of continuing to keep trying to turn until it gets to the actual heading that it should be facing. So if it tries to rotate to 0, but it ends up 1 or 2 degrees off, it'll just rotate back and forth until it gets to 0. Localization. To understand where the robot is on the map and enter the initial state, the robot begins by assuming that it is initially placed behind the first line on either side of the board. It moves forward to the line, and this gives it the predefined x coordinate because the line is the same on both sides. Then it turns 90 degrees and negative 90 degrees and measures the distance to the wall. And it does both of those turns just to make sure that it's not accidentally detecting an obstacle and getting too close to the wall. And the robot then uses these distances to calculate its y coordinate. So if the distance that it measures on both sides plus the size of the robot is greater than the total distance of the board, then it knows that it has a detection of an obstacle, and it can use those distances to define its y coordinate. Here's an example of that localization in action. You can see the robot is placed behind the first line, and it's perpendicular on the board, so the gyro sensor will be accurately calibrated. And then it moves forward to the first line, turns 90 degrees. And then I have it move to the middle of the board just to demonstrate that it knows where it is. Obstacle detection. To detect obstacles, the ultrasonic sensor mounted to the top of the robot scans the field every 100 milliseconds. If an obstacle is detected within 2.2 meters, its position on the grid is located, and it's determined whether or not the obstacle is known. And this is a rough estimation so that it can do it quickly. If the obstacle is not known, then a better estimation is done to figure out where the obstacle is on the map, and its associated nodes are removed from the grid mesh. The A-star path planning algorithm then uses the available nodes to find a path for wherever the robot's trying to go on the board. The ball detection is done similarly. The IR sensor is mounted to the front of the robot, but it's at an angle facing toward the board. When the robot is searching for the ball, it performs sweeping scans with this sensor. Objects close to the sensor that are not visible to the ultrasonic sensor are assumed to be the ball. So if the ultrasonic sensor can't see it, but the IR sensor can see it, then we assume it's the ball. A simple predefined path to capture the ball is then followed where it turns slightly, moves forward, and then closes the claw, and a path to the goal is found, and then it follows that back. And here is a full goal cycle for the robot. It's going to start by doing the localization, so it'll move forward and turn to the left and right to figure out where it is on the board. Now it's entered the initial state, so it's going to wait for a button press to start looking for the ball. and it'll move over to the right side of the board, and it'll move forward until it gets close enough to the middle of the board where the ball could feasibly be, assuming the ball is between the innermost green and blue line. Then it will start trying to find the ball, and whenever it detects it, it'll close the claw around it, turn back, and find a pathing algorithm to the goal area. And then it waits 5 seconds, and it will return to the initial state. And finally, here is the remote controller used for the remote version of the robot, which ours is a hybrid application, so this controller has to be used every time the robot is used. It has an autonomous mode button that you can start the autonomous mode with. It also, you can turn any number of degrees. Clockwise is positive, negative numbers turn counterclockwise. You can move forward a number of inches on the board or backwards, and then you can open and close the claw, or you can stop the program. All right, and that's it. Thanks.